For millennia, if not since time immemorial, cultures around the world have woven the sun into their understanding of reality. To some ancient Egyptians, humans were created from the sun god Ra's tears. In Viking mythology, Sol would cross the sky with her brother the moon, and in doing so help humanity tell the time. And in one Aboriginal Australian story, the Sun Mother is sent on a mission to a barren earth to awaken sleeping spirits and give them form as both plants and animals. And as science has advanced, instead of refuting these early notions, as the expanding of our horizons has cooled time on so many other ancient beliefs, it has become clearer and clearer that these myths are not so far from the truth. In many ways, the sun is our God. On the most fundamental level, the light of our closest star warms the surface and air, keeping temperatures within a narrow band so that water persists as a liquid. Photosynthetic organisms capture solar energy and convert it into their own source of chemical nourishment. Creatures who cannot produce their own food in turn consume this converted sunlight, powering their cells. Without it, our planet would be a lifeless, frozen rock, drifting in oblivion. But more than just this, there is something deeper at play. For we do not only receive energy from the sun's rays, but we are made up of its ancestors' remains. In ancient tales, sun gods were sometimes born from a more primordial deity. The Aztec god Huitzilopochtli came into being when his mother was touched by a ball of feathers that had fallen from heaven. Amaterasu, the Japanese sun goddess, was born from the left eye of her creator deity father Izanagi. And just as these legends hint at a lineage, so our sun is not the first. It was born from a stellar nursery filled with gas, the greater portion collapsing under the power of gravity until matter was dense enough, hot enough, to shine. And it is from this attracted matter that our Earth was born. But what begot these vast, latent nebulae? What created these scattered elements that make up us? Our sun is in fact the latest iteration of an epoch-spanning cosmic recycling, what astronomers call a population 1 star. It descends from other, now long-dead stars, which transformed the matter within themselves, forging new elements within their massive cores, before scattering their ashes in vast supernovae. Like the sons and daughters of solar mythology, our sun was born of an older source of light. But it was not simply a clone of its parents. Its chemical composition is very different to those that came before, a byproduct of its ancestors' life cycle. While some of these older stars must die to seed the universe, many of the less massive stars from this generation persist to this day. In the Milky Way, population 2 stars reside primarily in ancient clusters outside of the galactic disk, in what is known as the galactic halo. And these stars, too, had ancestors of their own, receiving their constituents from the most ancient suns, with the most pristine of ingredients, the purest of mixes. The yet-to-be-observed population 3 stars, the very first to be forged in the universe. But again, these were not the first cosmic cradles of creation. For the ingredients of these enigmatic giants were created in the very first seconds of time, a brief instance when the entire universe was hotter than the sun's core. It was once said that we are star stuff, but that is only half the story. The no-hair theorem states that black holes only have 3 properties: mass, angular momentum, and electric charge. Nothing else can help differentiate them. And as Albert Einstein, James Clerk Maxwell, and Max Planck can attest, your hair or a well-shaped moustache or beard can certainly help you stick out in a crowd. Henson Razors have been kind enough to support this video, and they are the cutting-edge razor makers, having switched in 2020 from making aerospace parts, including for the actual International Space Station and Mars rover. They have taken that precision, expertise, and need for perfection into the world of razors. In fact, they've convinced me to switch from using my terrible electric razor, and I feel much better for it. They're also totally plastic-free and should last for decades, and in the long term, because they basically never break, they should save you lots of money. The blades are only 10 cents and you can get them easily on Amazon, meaning that it's barely $5 a year to maintain. So click on the link in the description to get 100 free blades with the purchase of a razor and start having a nice, smooth face. Thanks to Henson for supporting educational content on YouTube. The year is 1782. A recent inductee to Great Britain's Academy of Sciences, the Royal Society, makes a claim that, if true, would answer centuries, if not millennia, of scientific inquiry. 30-year-old James Price had discovered a way to turn base metals into gold. More specifically, Price claimed that he had developed a white powder that could turn a gram of mercury into 50 of silver, and a red powder that could turn the same mercury into 60 grams of gold. But unlike your run-of-the-mill charlatan, Price had performed experiments that backed up his implausible claim, with witnesses. While his fellow chemists at the Royal Society remained unconvinced, the University of Oxford saw fit to award him an honorary medical degree for his labours, not explicitly for these experiments, but perfectly timed to suggest they played a factor. To the greater public, Price had finally demonstrated that alchemy was more than magic. It was science. But as his fellow Royal Society members demanded a replication of these experiments for their own eyes, Price quickly grew reluctant. He claimed the creation of the powders was too strenuous on his health, and that the process would never be financially profitable. The value of the silver and gold created did not exceed the value of the materials put into making them. His reputation as an honourable chemist, he claimed, should be enough for his peers to take him at his word. Buckling under the pressure, in January of 1783, Price finally agreed to the Royal Society's demands. Of course, Price knew he was unable to prove his implausible claim of alchemy, and so, instead of turning mercury to gold before the eyes of the gathered fellows, he drank a vial of concentrated laurel water and died. But the human desire to transmute one element into another did not die with him. Modern tales of this desire tend to stem from one man, the so-called father of nuclear physics, Ernest Rutherford. Born in Britain's New Zealand colony in 1871, Rutherford escaped the small, single-teacher town of Havelock at the age of 15, eventually making his way to the University of Cambridge as the first non-graduate of Cambridge to earn a spot as a student researcher. Not long after the discovery of radioactivity, Rutherford set his sights on the new field and set up a lab at McGill University in Canada to investigate these mysterious new compounds. During one such observation in 1901, Rutherford and his English colleague Frederick Soddy caught a sample of solid thorium slowly converting into radium gas. Soddy excitedly exclaimed the thorium was naturally undergoing transmutation, the changing of one element to another, to which Rutherford supposedly responded, "For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists." Rutherford's aversion to the term aside, this was a huge moment. Would the pseudoscience of alchemy edge its way into reality? By the 1920s, Rutherford had demonstrated that by bombarding nitrogen atoms with alpha particles, he could create hydrogen. And in 1925, to prove it once and for all, he tasked his student Patrick Blackett to photograph the disintegration process using a tool known as a cloud chamber. Definitive proof that nitrogen could be changed into oxygen. Blackett had done what James Price could not. Even though it wasn't silver or gold, he had intentionally turned one element into another. Blackett was awarded the Nobel Physics Prize in 1948. Alchemy was possible, if not what the ancients had envisioned. Rutherford would go on to say, "It is now possible by modern methods to produce exceedingly minute quantities of gold, but only by the transmutation of an even more costly element, platinum." The 20th century had thus ushered in the era of the subatomic. Atoms were not, as their Greek name suggested, uncuttable. Elements became defined based not on their overall mass, but on their proton count. Transmutation, therefore, merely required that proton count to change, and such a feat was possible through several means. The first was through natural radioactive decay, which required no human input whatsoever. An unstable nucleus would emit a particle, thus becoming a lighter element. The second was nuclear fission reactions, wherein human influence triggered an already unstable atom to crack apart, be it at a nuclear power plant or within the heart of a nuclear bomb. And finally, through the process of nuclear fusion, the combination of two or more atomic nuclei, a power which humanity has yet to truly harness. Atomic nuclei, being composed of protons and neutrons, are positively charged, and as we learn from our first exposure to magnets, two positive sources of electromagnetism repel one another. The closer two nuclei get, the stronger the urge for them to fly apart. But there is another force which can come into play. The strong nuclear force binds protons and neutrons together, but its strength drops dramatically beyond the edge of a nucleus. Therefore, scientists must generate enough force to push two nuclei close enough together that the strong force can take over. In the core of our Sun, this is achieved at a temperature as low as 15 million degrees Celsius. But on Earth, where we lack the crushing pressure of the Sun's continually gravitationally collapsing matter, we need to get our fuel even hotter, at least by 10 times. A full century after the discovery of nuclear transmutation, today's scientists are still pursuing the quest to imitate the immense power source that maintains our Sun's billions-of-year lifespan, and created many of the elements that make up the universe. The quest for man-made nuclear fusion. What is the source of the heat which the sun and stars are constantly squandering? In 1920, English astronomer and physicist Arthur Eddington posed this question to his peers at the annual meeting of the British Association for the Advancement of Science in Cardiff. Scientists of the day would answer the question with gravity. The collective collapse of the gaseous matter from which the sun is constructed would generate a release of heat, just as the rocks and metals of the Earth did, a leftover energy set in place when the solar system first collapsed into its various orbs. But these same scientists also knew that answer could not be correct. The age of the Earth, and by extension the solar system, was already known to be in the billions. But at the rate with which the sun shone, it would have run out of energy to release in a mere 20 million years. Eddington asserted that it was mere tradition that kept this hypothesis alive. Or rather not alive, he wrote, but an unburied corpse. Instead, he looked to the burgeoning field of his contemporary Rutherford for a new answer. A star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than subatomic energy. Eddington speculated that deep within the sun, hydrogen was turning into helium, and perhaps even heavier elements, and releasing energy in the process. Indeed, it was the stars themselves that operated as cosmic factories. Eddington estimated that through the subatomic, the sun could shine for 15 billion years. While that estimate turned out to be several billion years in excess, Eddington's concept of stellar nuclear fusion was spot on, and he went beyond proposing merely how all stars shine, but what that meant for humanity. The possibility that we could harness nuclear fusion for the well-being of the human race, or for its destruction. And over the past 100 years, scientists have worked towards at least one of those fates. And it turns out, the key to exploiting the power of the sun may lie in imitating its weaker sibling. Brown dwarfs are often called failed stars. They are so dim that they elude capture, but scientists believe that for every true star in the universe, there may be an equal number of brown dwarfs. They are the intermediaries between gas giants like Jupiter and the smallest stars, failing to accrue the mass necessary to begin the process of fusion all true stars do, specifically the ability to fuse lone protons, what we typically describe as hydrogen, into helium. But brown dwarfs are capable of another kind of fusion. They merely require a different kind of hydrogen. Deuterium is the lightest composite atomic nucleus, meaning it consists of more than one nucleon. Like all hydrogen, it has one proton, but bound to that proton by way of the strong nuclear force is an additional neutron. The abundance of deuterium depends on where you search. In Earth's seawater, there is approximately one deuterium nucleus for every 5,000 or so hydrogen nuclei composed of only one lone proton, known as protium. Meanwhile, in the atmosphere of Jupiter, the ratio drops to 1 for roughly every 40,000 protium atoms, far closer to the true ratio of deuterium to protium across the greater universe. And it is this deuterium that brown dwarfs are capable of fusing with protium. This is because the presence of that single neutron makes it slightly easier for the nuclei to overcome their mutual electromagnetic repulsion. Less energy is required to fuse them together. As deuterium is naturally abundant in seawater, with only 1 liter of water capable of generating the equivalent amount of energy as burning 300 liters of gasoline, scientists on Earth have turned to this isotope as a possible way forward into fusion technology, a type of alchemy where the most valuable product is not the proverbial gold made from lead, not the helium made from hydrogen, but the energy released in the process. Price and his alchemist predecessors would stand utterly confounded by the machines we use today to transmute matter. In one pioneering experiment, this is the modern version of his lead, a microcapsule of synthetic diamond placed within a golden cylinder roughly the size of a pencil eraser. This capsule is cooled to temperatures just above absolute zero and placed at the center of a giant spherical chamber 5 meters to the inner edge. And it now becomes the target of 192 ultraviolet lasers. In far less than the blink of an eye, these lasers impart a pulse of invisible energy to the capsule. It disintegrates its diamond coating, inducing an implosion to heat the contents inside from all sides, with so much intensity that humanity can harness the vast power of a brown dwarf. This is the National Ignition Facility, or NIF, in California. The most efficient way for humans to go about turning hydrogen into helium fuses deuterium not with protium, but with tritium. Tritium is, as the name suggests, a third isotope of hydrogen. 1 proton, 2 neutrons. Together, they yield a nucleus of helium-4, the most abundant form of helium, and a lone neutron. And 80% of the energy liberated by the fusion process is carried by that neutron. In August of 2021, a single NIF experiment fused roughly 200 micrograms of deuterium and tritium to produce an equivalent of 10 quadrillion watts of power, roughly 700 times the output of the United States' entire electrical grid. However, it could only be sustained for 100 trillionths of a second, meaning the actual amount of energy it created was just enough to power a light bulb for 6 hours. Still, this experiment also claimed the world record for the most energy-efficient fusion reaction. 70% of the energy they put in came back out. But for comparison, this is only an additional 3% above the record set for deuterium-tritium reactions nearly 25 years earlier. And of course, to ever be a source of power, it must exceed 100%. And so, this NIF experiment illustrates two major hurdles scientists must overcome before nuclear fusion can be incorporated into humanity's power-generating infrastructure. First, a reaction must produce more usable energy than it consumes. While the deuterium-tritium reaction is easier to achieve at the outset than it is with other nuclear fuels, it is more difficult to convert the byproducts of that reaction into electrical power. This is because the vast majority of the energy generated by the fusion reaction is carried away by a neutral particle. The second challenge is that the reaction must be sustained for sufficient lengths of time. The International ITER project, based in France, claims that it will be the first project to create net positive energy through nuclear fusion. More specifically, the group hopes to produce 10 times the amount of energy that they put into making it. However, even if it succeeds in its goals, the energy it generates cannot be captured. It will be up to yet more experiments to harness deuterium's power. It is clear that the deuterium-tritium reaction is not the perfect solution to humanity's energy woes. Other kinds of nuclear fuel, such as helium-3, offer a cleaner alternative, while being more difficult to fuse. It is thought that our moon may hold a treasure trove of this isotope, built up over 4 billion years of being bombarded with individual nuclei ejected by our sun. Assuming the technology can be developed to create positive net energy from such a fusion reaction, the question becomes whether or not certain areas of our moon have helium-3 in sufficient quantity to justify mining it as a resource. We may yet see ourselves in the middle of a second space race. As science continues its stare down with the challenge of sustained nuclear fusion, humanity's modern alchemists hope to one day recreate the processes stars are capable of doing all on their own. Processes that over billions of years of death and rebirth have created nearly all the elements we see today. But there was a time when stars were not needed to fuse nuclei together. Before brown dwarfs, supernovae, or even population 3 stars, there was a brief moment in which our entire universe was a fusion reactor. Why would a person throw themselves into a volcano? If you are the 5th century BC philosopher Empedocles, it might be to try and convince your followers that you are a god. Indeed, the myth of Empedocles' death is just that. Despite this, surprisingly, today he is most well known for a singular proposal, originating in his poem Periphysios, or On Nature. As the title hints, Empedocles sought to identify the very makeup of the universe. Only fragments of the poem still remain, but the thoughts expressed have permeated Western culture well into modernity. Empedocles proposed that every observable substance in nature is composed of some combination of fundamental substances he called rhizomata, or roots, which he attributed to 4 deities. Today, scholars generally translate these as fire, earth, ether, and water. Plato then replaced the term roots for stoicheion, which in English we call elements. While Aristotle would say that Empedocles was the first philosopher to distinguish the 4 elements, even modifying the hypothesis to include air, other cultures had certainly formulated their own versions of a similar concept. Around the world, humans were realizing that everything we can sense in the universe is actually, when you break it down, made of more fundamental building blocks. Today, we know of 118 elements, most frequently organized into a table which shows the periodicity of certain properties. The heaviest of these elements do not exist in nature in any measurable quantities due to their incredibly short lifespans, and the vast majority are made in the violent deaths of stars and stellar remnants. Through various different reactions inside stars, scientists have been able to account for a lot of the elements that make up our world. But for many heavier elements, our sun is just not big enough. Carbon and oxygen require a star around 1/2 to 4 times the mass of our Sun, whereas more than 4 times the mass and the star can fuse oxygen to silicon, and the creation of iron within the core of a star more than 10 times more massive than our Sun acts as a metallic death knell for its host, a sign of imminent supernova. So how can we explain a universe rich in far heavier metals? One answer is in the brutal supernova that scatters those elements across the cosmos. Many heavier elements are believed to be formed in the energetic chaos of a star tearing itself apart. Another is in slow neutron capture in certain types of stars over thousands of years. But yet another solution may lie in an event even more violent. In 2017, the newly operated LIGO Laser Interferometer Gravitational Wave Observatory detected 2 neutron stars colliding. Neutron stars are the densest thing before a black hole, the dead heart of a massive star, and using the previously inaccessible medium of gravitational waves, ripples in the very fabric of space-time, LIGO was able to pick up the faint echo of a circling pair's final moments. But their detection was just the beginning. The scientists were able to use information from LIGO to focus other instruments on the kilonova event that followed the merger, and through reanalyzing the spectroscopic data in the explosion, detected a heavy element. Strontium, with the atomic number 38. Proof that the most catastrophic events in the galaxy are responsible for at least some of the heavier elements. And so, the explosive demise of these stellar objects gifted us with the various elements that make up the world we know today. But what gave them life in the first place? What made up the first stars? As with their heavier cousins, these primordial elements arose in an instance of vast, cosmic violence, the most energetic moment in the history of the universe. The Big Bang. In the very first moments of our universe, a soup of fundamental particles and antiparticles sprung forth from a sea of energy. With rapid expansion came rapid cooling, though temperatures were still incomprehensible to mortal minds. 10 trillion degrees Celsius as the first microsecond came to its end. Still, it was now cool enough for lone quarks to bind together into composite particles we call hadrons. While we know of 6 flavors of quark, only 2 govern our daily lives. Their names, however, fail to convey their importance. They are merely known as up and down. Combine 2 up quarks and 1 down quark and you have made a proton. As all hydrogen atoms are defined by a proton count of 1, these were the first hydrogen nuclei. Meanwhile, each neutron is born of 1 up quark and 2 down quarks. Together, these 2 hadrons provided the necessary ingredients for Big Bang Nucleosynthesis, the distant ancestor of every star, every planet, and every life form alive today. The process of Big Bang nucleosynthesis was first described in 1948 by then graduate student Ralph Alpha and his supervisor George Gamow. A third author on the paper, Hans Bethe, was added by Gamow as a joke. The Alpha Beta Gamma paper was born. In this paper, Alpha predicted that the incredibly high temperatures and pressures found at the origins of the universe could induce a multi-step process of nuclear transformation. Hydrogen, the only element then in existence, would become helium for the very first time, and the first step in this alchemical process was to synthesize deuterium, the bonding of 1 proton and 1 neutron into hydrogen's second isotope. While protons and neutrons had existed in equal quantities when hadrons first formed and could just as easily transform from one into the other, time was proverbially waiting for no one. Temperatures kept dropping, making it harder to craft neutrons. Neutrons, it turned out, were ever so slightly more massive than protons, and that extra mass meant slightly more energy was required to create them. Additionally, neutrons were less stable than their positively charged counterparts, as they continue to be today. Powered by the weak nuclear force, a lone neutron will eventually undergo radioactive decay, becoming a proton, electron, and anti-electron neutrino. By the time the universe was ready for nucleosynthesis, there was only one neutron for every 7 protons, a ratio which utterly shaped the subsequent 13.8 billion years of the universe's evolution. While deuterium could form just a few seconds after the Big Bang, it was still so hot that if a stray particle of light hit a deuterium atom, it would break apart. Scientists call this the deuterium bottleneck, and it meant that, for at least a time, nucleosynthesis could not move beyond a single element, could not progress onto or past the fusing of one neutron and one proton. But somewhere around 300 seconds after the Big Bang, that bottleneck widened. Deuterium could finally exist without the threat of breaking down from a stray photon, and by then, the universe was well into the process of creating helium. There was, however, a ticking clock. The universe was cooling, expanding. Just how many elements could the universe birth in the brutal heat of its own creation? Once there was roughly one deuterium nucleus for every 100,000 lone protons, they too engaged in nuclear fusion reactions, the process still used today, at least briefly, by the brown dwarfs hiding in our night sky. And it was from this union that a second element finally arose. Helium-3 nuclei, constructed from 2 protons and 1 neutron. While hydrogen can exist without neutrons, helium cannot. Its 2 protons exert a mutual positive force that threatened to tear the nucleus asunder. As such, there was no way for 2 lone protons to create helium on their own. But with just 1 neutron, there was enough pull from the strong nuclear force to overpower the electromagnetic push. A helium-3 nucleus, whether made at the dawn of the universe or by a stray cosmic ray in the modern day, is stable. Left alone, it will persist until the end of time. However, the most abundant form of helium is helium-4. 2 protons, 2 neutrons. In this early universal forge, helium-4 arises mostly from the union of a deuterium nucleus with one of either helium-3 or tritium. And with helium-4 came the most stable composite nucleus in all of existence, the most difficult to break apart. In nuclear physics, it is the simplest of the nuclei we call doubly magic. If the early universe preferred the proton over the neutron, it preferred the helium-4 nucleus over all others, save protium. The march of time therefore dictated that in these first few minutes, most of the protons and neutrons in the universe that began the process of nucleosynthesis became trapped inside helium-4 and went no further. Together with the overall density of matter at the time, the ratio of protons to neutrons restricted just how much helium could be made. If matter were more compact at the time of Big Bang nucleosynthesis, more helium would have formed. Perhaps so much helium, the least reactive of all the noble gases, that little to no chemistry may have ever happened throughout the rest of time. We often say that the early universe was 75% protium and 25% helium-4, specifically when measured by mass. Photons, neutrinos, dark matter, and so forth are not incorporated into this statistic, but it is an important one, as it is also the composition of the very first stars. And these are the population 3 stars, which astronomers continue to hunt for. But hydrogen and helium are only 2 of the 118 elements in our modern periodic tables. Where did the rest come from? The universe keeps cooling. Fusion continues. Next up, 3 protons. This is lithium. In Big Bang nucleosynthesis, 2 isotopes are created, lithium-6 and lithium-7, the latter in greater abundance. Beryllium is next with 4 protons, but it is unstable, decaying into lithium in an average of 53 days, and beryllium-8, meanwhile, exists for less than a billionth of a second. Indeed, no isotope composed of 8 hadrons is stable. And so here, nucleosynthesis hits another bottleneck. With fewer heavy nuclei in abundance and with ever-dropping temperatures, it becomes almost impossible for the universe to create an isotope with at least 9 hadrons. If any boron, carbon, nitrogen, or oxygen were crafted, it was in such limited amounts that there is no record of the universe having done so. Finally, 20 minutes after the Big Bang, the nuclear furnace that spans the entire observable universe dies. Only 4 elements exist, and only 3 exist long enough to see the first stars shine: hydrogen, helium, and a trace amount of lithium. It would be at least 200 million years before the universe had another opportunity to seed itself with heavier elements, when blazing spheres of hydrogen and helium compressed their cores with sufficient force to achieve the temperatures long missing. But it is through those stars, or rather their descendants, that we must piece together the state of the universe at this ancient time. And in doing so, scientists have discovered a mystery that lingers at the heart of this lineage of celestial bodies, an imbalance that threatens our understanding of the entire timeline. In 2013, astronomers made an impossible measurement. Observing a star which had been an occasional target for at least a century, they finally pinned down its age. Or did they? At first glance, this star appeared to be older than the universe, 14.5 billion years old. And it was located only a mere 109 light-years away in our own solar neighborhood. Its designation, HD 140283, but in popular media, it became known by the biblical name, Methuselah. Of course, it was far more likely that there was some kind of error made in either the measurement taking or in the fundamental understanding of how these measurements correspond to a star's age than it was that the ancient star was born before the known universe. And indeed, when the team accounted for the various uncertainties in their measurements, the minimum possible age became 13.66 billion years. Methuselah was not older than the universe. Further research published in 2021 suggests the star may be even younger, as young as 11.5 billion years old. Calculations completed this past decade still suggest a wide array of ages, though all within the first billion or so years of the universe. So we may never know its true age, but its composition does tell us something crucial about cosmic history. Based on the abundance of metals in Methuselah's atmosphere, astronomers know that it was not one of the very first, but instead formed soon after stars from the first generation died. Stars, like the Big Bang before them, go through their own version of nucleosynthesis, both during their lives and at the moment of their deaths. This means that the abundance of metals, be it iron or oxygen, increases amongst all subsequent generations, forcing us further and further away from the image of a universe before any stars at all. Population 3 stars, with metallicities as near to 0 as the universe allows, gave birth to population 2, with metallicities of roughly 0.1%. And through their lives and deaths, they eventually, in turn, gave birth to those stars classified as population 1, with metallicities in excess of 1%. Methuselah appears to be one of the most ancient population 2 stars, and it is this generation which astronomers have been forced to study to try and confirm what models predict the original elemental abundances after Big Bang nucleosynthesis ended, and the composition of the ever-elusive population 3 stars. Astronomers also look beyond individual population 2 stars in their attempts to extrapolate back to even more ancient days. They turn to the least massive, irregularly structured dwarf galaxies, that contain them. With less mass, there is less hydrogen to collapse and form stars. So, due to their relative lack of star formation, these minuscule galaxies tend to have the lowest metallicities, and so they are the closest proxy to the abundance of elements in a time before stars. Measuring a galaxy with near zero metallicity implies the amount of helium has not been altered through stellar nucleosynthesis. The abundances of hydrogen and helium mimics the ratio found in the first half hour of the universe, hundreds of millions of years before the very first stars. Indeed, there is little disagreement between the abundances of hydrogen, including deuterium and helium-4, in these only slightly less ancient days, compared to the primordial levels predicted by mathematical models. Lithium, however, is a trickier matter, a mystery science has yet to solve. Stars, it turns out, are particularly good at destroying any lithium inside them, be it what they formed with or what they made along the way to heavier metals. Thus, they obscure the story of how much lithium was created in the Big Bang's metaphorical forge. Nevertheless, by narrowing in on how readily lithium is both created and destroyed, observations of population 2 stars, in particular the oldest, hottest stars we can find in the Milky Way's halo, can still provide estimates. But these estimates do not match what other analyses imply. According to current astrophysical theory, the amount of lithium crafted after the Big Bang, as well as every other primordial element, is ultimately dependent upon a single variable: the ratio of photons to protons and neutrons at the moment Big Bang nucleosynthesis began. By looking at the cosmic microwave background, which reveals the oldest light our telescopes will ever see, astronomers can measure that ratio and therefore predict, according to the known laws of physics, how much lithium-7 should have been created. But that expected value is roughly 3 times greater than what is actually observed. Astronomers have given this unique discrepancy a name: the cosmological lithium problem. And there are 3 possible solutions. The first looks to the stars, the measurements we take of them, and the equations describing their inner workings. Only the outer layer of a given star can be observed, so some of the apparently missing lithium may be concealed at a greater depth, or used up in the fusion process that our current physics cannot depict in full. But astronomers are also not directly measuring the abundance of all lithium-7. Some must be inferred given the local temperature. However, determining the temperature of any one spot within a star is rather more complicated than it might seem at first glance, so a small deviation from the true temperature manifests as a much greater error in the amount of lithium astronomers believe they must add to what they already do detect. A second solution is found at the nuclear level. Specifically, the ease at which different nuclei interact with each other, bind together, or break apart may not match our current understanding. For example, since primordial lithium-7 is created by the decay of beryllium-7, if it were actually harder for beryllium-7 to form than our models suggest, or less likely to decay into lithium-7, that could explain why we observe a lower quantity of primordial lithium. A team of researchers considered this possibility in 2015, but their analysis created an even starker divide between observed quantities and theoretical ones. And finally, it may be that our theories that describe the nature of reality paint an inaccurate picture. Our underlying assumptions for not just Big Bang nucleosynthesis, but for all astrophysical processes are incomplete at best. The theoretical abundance of all the primordial elements stems from cosmologists' understanding of the fundamental processes of reality. The 4 fundamental forces of gravity, electromagnetism, and the strong and weak nuclear forces, the expansion of space, the properties of subatomic particles. It also depends on the state of the universe in those early moments, its size, temperature, and density, and how rapidly each of those is changing. Indeed, we already know that our models are inaccurate in specific matters, such as the fact that neutrinos actually have mass, or that dark matter almost certainly exists and is likely made from particles which remain unaccounted for in the standard model. Exotic particles which existed at the dawn of time but no longer, or still existing particles we have yet to discover, could have tipped the scales in a process we are, as of yet, blind to. Or perhaps it is the universe as a whole that is not what we think it is. The cosmos is assumed to be homogeneous over large scales. Our position in the universe is no different, no more special than any other position stretching across billions and billions of light years. From each world, alien astronomers would measure the same overall structure. But what if that weren't true? If our region of the cosmos was in fact special, say a little less dense than the overall average, the measurements we take may be biased. Only time, of course, will tell. With more advanced telescopes, more sophisticated computer systems to crunch the numbers at finer details, scientists may one day resolve this primordial lithium problem. Perhaps it is simply a matter of our current methods being insufficient to fully capture the true nature of the universe. Or perhaps the true nature of the universe is itself something other than we imagine. And so we continue on, to try and comprehend how our universe went from an energetic soup of a handful of fundamental particles to the vast cosmos we see, experience, and take part in today. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.